There we go. Okay, so we're going to be starting module 4 now. So let's kind of look at what we've got coming up here. So the first thing that we have here is our learning plan. So we'll kind of go back to that. You'll also notice that we have our session recordings. I do have session recordings from last year because I taught this class at WCTC here last year. So you'll notice that there are some videos out here. So if you wanted to, look at those or see what's out there, it's going to be the same content that we're going to be covering here, but it's there if you so choose. We have practice problems. Okay. Now our practice problems here, it looks like it's a lot. And this is a little bit longer module than the last two that we've been looking at because there's some new material. But the examples that you see here are all found in the guided notes that I have, okay? And the guided notes are, if you're in the classroom, they're going to be here at the end of the desk, so you can just fill this along with me as I go through the class. Or if you are virtual, the guided notes are right here, okay, in the learning plan. So if you click here on the guided notes, this is going to be the handout that we're going to be going through. I'm going to have it underneath my camera and we'll be filling in blanks and we'll be doing the examples and such that kind of come along here. So it's a little bit more detailed than just taking notes. So if you are virtual and you don't have a printer handy, then my expectation is you're kind of following along and kind of, identifying the things that we're doing in addition to the examples. And then finally, our practice problems prepare us for the application problems that we see here. And there's some application problems here. All right. So so as we work through, you'll be getting prepared to work those. So application problems we'll kind of look at as we go along. So I'm going to go back to our learning plan here. Now, this particular chapter or this module, we are going to be using a handout for the chapter. Our book does not take time to just look at this subject. And I think it's very important in kind of, going through the process. So what I did was I took this out of a textbook that I used to use, and that is the chapter that you see here. So there won't be anything in the electron or the ebook that you have through McGraw-Hill. Instead, this is the PDF of the chapter that I'll be referencing as we go through. I happen to have mine printed out. I don't think you need to print out the whole chapter. I'll be referencing some of the examples or some of the figures as we go along, but really the guided notes are going to be what you want to kind of focus on here. Whoopsie. Okay. So the reference to the chapter. So any page numbers down here and examples are coming from that PDF, not from our McGraw-Hill ebook. Okay. So anything in this module refers back to this chapter and the guided notes. All right. So what I'm going to do is I actually have both of those underneath my camera. So I'm going to go underneath and this is what the chapter looks like. So like I said, I just kind of, copied the chapter down or copied the chapter and printed it out. And then my guided notes go along with the sections and the page numbers and such. Okay. So as we start looking here at this chapter 4, this chapter is called Resultant of Non-Concurrent Forces in a Plane. So what this means to us, if you recall, in modules 2 and 3, we were always dealing with concurrent force systems. That meant that, that just simply meant that the forces that we were looking at all shared a common point, whether that was moving them along their line of action, principle of transmissibility, or they were physically connected at that point. Okay, so we saw everything, if you would, come together at the origin of our X and Y for the problems that we've been looking at. That's a concurrent force system, forces that share a common point. This is a non-concurrent force system. So this means they don't share a common point. So we've got to deal with those. Okay. So, and then in a plane just means that we're dealing with the X and Y axes, not the Z axis. Okay. So first of all, we're going to revisit, and we've talked about this before, that principle of transmissibility. So the figure that we see down here, 4-1. You'll notice that we have point A, we have force F, and you're going to notice it's on I'm going to say in quotes, a rigid body. They're just showing an oval here. And they're showing the application of that force at point A. Now, you'll notice that there is a dotted line here, and they're pointing to it, and they're saying that's a line of action. So if we go over to part B on this figure, you're going to notice that that same force shown the same length, assuming that it is the same magnitude along the same line of action, is just move to point B. As we know, and as we've visited, but formally now looking at this, the principle of transmissibility says that we can move a force anywhere along its line of action, and it will have the same net effect on the body. So if we look at force F at A, it's pointing up and to the right. So that means that it's on the body. So it's going to be moving that body up and to the right, whether it's down towards the bottom of the rigid body or up towards the top, where we can maybe say it's pulling on the body. The body is still going to have the tendency to react in a way that it's going to move, if you would, up and to the right. So whether it's applied down here at point A or up at point B, the same net effect, we call it, on the body will occur. Okay, so the principle of transmissibility says we have the freedom to move these forces anywhere along their line of action, and we're not going to change the problem. Okay, as long as we keep them on their line of action, right? So that's what we're looking at here. Now, in our guided notes at the very top here on page 1, okay, so for those who are virtual, if you want to kind of identify this as page 1, the very first blank that we see here, it says the principle of transmissibility states that a force can be moved along its 3 words, blank, 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 and still have the same net effect on the body. What would we fill in those 3 words? Along its line of action. Yes, line of action is how we would fill that in. So we're going to put in here line of action. Okay. And again, that's that figure that we just looked at on page 64. And if we turn the page, it looks like there's another one that we can look at, and it's going to have that same idea. So in this case, we have a rectangular block, if you would. We've got force A, or a force on point A, a force on point B. We can move those again at any point along that same line of action. Since they share the same line of action, notice that we moved the force from point B to point A, same net effect. Okay. And as we look at them here, they look like they're probably the same magnitude because they show like they're the same size. So I would assume that they're in equilibrium, if you would. One is pulling to the left, one is pulling to the right. They kind of cancel each other out. Same net effect on the body. Okay. All right, the next section here is looking at the moment of a force. So a moment, okay, a moment, this might be a new term to you. A moment is the tendency of the force to produce a rotation, okay, about an axis, okay, about an axis. The moment of a force about an axis is defined as the product of the force and the perpendicular distance from the line of action of the force to the axis. Okay, so what does that mean? So rotation is the first blank, perpendicular is the second blank, okay? So if we go down to the bottom of page 65, we kind of have a classic example of a wrench that's tightening or loosening a bolt, okay? This would be loosening, it's lefty, no, it's righty tightening. So it looks like it's tightening up that bolt. Now, in this case, you're going to notice that we have a force, okay? That force, it's coming in at an angle on A, which it happens to be on the handle of the wrench. The center of rotation is going to be the center of the fastener, in this case, that we're trying to tighten. Now, to calculate the moment, okay, moment is going to be taking the magnitude of the force. We would have to know what the, how many pounds, how many newtons that might be. And we're going to multiply it by the perpendicular distance to the line of action. So if we extend this along that line, you can see how I kind of drew that longer. And then we found from point A, we found the perpendicular distance. So 90 degrees, we would know what that value is. We can multiply this distance times this force, and we get the product of the moment. Force times distance. Is there any other thing that you know of that's kind of similar to that? Moment, or what? Has anybody ever seen anything where it's a force times distance? What?
Momentum?
Not momentum. Starts with a T. Torque. Yes. Torque is going to be multiplying force times distance, but there is a difference between moment and torque, and that's why I like to differentiate here. In the case of a wrench or that's going to tighten a fastener, yes, we talk about the torque rating or what is the torque going to be? And we say, oh, whatever it is in foot-pounds, right? Or something like that, or in inch-pounds. When we talk about moments, moments are going to be rotations that are created from offset points or axes for items that aren't intended to rotate. So when we are in statics, we're usually looking at things like frames or beams or shafts. And where they're supported, we want to find, what those reactions are. That's going to be something else that we calculate. Well, we're going to find that we have to calculate moments because there are going to be tendencies of offset forces to cause rotations, but they're not intentional. When we have intentional rotation, really like we see here, this is an application of torque. Okay, we're going to calculate it as a moment, but it's a nice example to relate to. But I want you to know that there is a difference. Although we calculate it the same, moment and torque are different, okay? And it's in their application. Moments are going to be calculated for the tendency of a force to cause a rotation when the item isn't intended to rotate, okay? It's more of a support. Torque is when we're actually seeing something rotating and the intention is to rotate about an axis, all right? As we see more and more applications through the program, you'll kind of see that difference. Okay, so force times distance. So as we look back over here at our guided notes, when we want to calculate a moment is going to be the capital M is called a moment, okay? Capital M, so you'll always see it as capital M. Sub-zero, okay? Zero is going to be the point that we're identifying that we're summing around. So it might be an origin, it might be a point A, it might be a point B, but it's going to be capital M sub whatever point we're summing our moments around, okay? And then to calculate a moment, F is going to be the force that we're applying. And D is going to be the perpendicular. I'm putting the perpendicular sign here, perpendicular distance. Okay. So that'll make more sense when we start doing some more problems. So perpendicular distance. So again, a moment has a tendency to cause a rotation about an axis or a point. And to calculate it, the product is going to be force times the perpendicular distance. Okay. Now, when we look at moment, we're going to be multiplying force times distance. Force times distance. So as we look at this equation, the units, what are you expecting for units of force? Tell me what units of force would be. Anything. English units. What are English units for force? I heard what? Oh, nope, that's pressure. Just force. I heard it over here. Pounds. Pounds is going to be units. Well, also the other units that we see for force are going to be kips. Anybody ever hear of a kip? A kip is 1,000 pounds. Okay. So English units are going to be for force, pounds or kips. And then English units for distance. What would we expect? No, in the chat box, we can put them in there as well for those who are virtual to stay active. I heard feet. Yes. So you could have pound feet. What else could you have? What's another distance in English? Feet. We don't hear yards often, but you could have a pound yard. What else? Probably a pound foot or a pound inch is usually what we're looking at. So for English units, the units are going to be pounds times. Notice the equation. It is not pounds per, it's not pounds divided by distance, it's pounds times distance. So pound inches, pound times feet, okay? Those are going to be your units. So when you're giving me the units and when we're, putting them in, we're going to be putting our units in all phases of the problem. And our final answer when we're calculating moments will always be pound inches, pound feet, kip inches, kip feet. Okay.
Is there ever a possibility for pound miles?
No.
Never that large?
Not in mechanical design. You're not going to come across that. Usually it's going to be pound feet, pound inches, kip feet, kip inches. Yeah, that's what we deal with. Yeah. But it could, I guess. It is a distance, but practicality wise, in our program now. No. All right, metric units. What are metric units for force?
Newtons.
A Newton, yeah. Newton, kilonewton, Those are going to be units. And then again, it's still force times distance. What would be a distance? Newton meters. Newton millimeters. Newton centimeters. Okay. So, and again, it could be kilonewton meters, kilonewton millimeters, kilonewton centimeters. So force times distance. Notice it's not a per in there. Okay. It's not because we didn't divide force by distance. We multiplied. So our units are derived from the equation. Okay. All right. Questions so far? This is fun. It's kind of like a workbook. I sprinkle these in. I don't do them all the time. All right, theorem of moments. Let's look at figure 4.3. Okay, that's down here. Okay. Now, as we saw with our wrench example, we saw that the moment is going to be equal to force times perpendicular distance. So in some cases, we might have to, kind of figure out what that perpendicular distance if it's not directly given to us. So in this case, we would kind of have to create the triangle, figure out the distances with some more information that we have here. And that's okay. That's going to be part of, what you might have to do for that. Another way that we can deal with these is if we have a force at an angle, we've already have experience breaking those forces into X and Y components. And now our distances are going to be perpendicular, if you would, along the actual axis of the wrench to the Y component rather than dealing with, if you would, the hypotenuse. So depending on the problem and depending on how you want to calculate, how you want to figure it, if you have forces that are at angles, breaking the components is probably something we're going to consider as we solve these problems. Okay, we would get the very same answer. Our math in this case would be done on the distance side. In this case, our math would be done on the component side. So really it's if you would, a horse apiece, how we solve for it, we'll still end up with the very same answer. Okay. So in this case, it says, our next, it is on page 2, break the force into X and Y components. So in this case, the Fy has a blank distance from the origin and is used to compute the moment. So if we look at our Fy in that example, Fy is right here, okay? It has a perpendicular distance. So notice that there's a right angle here, and this is going to be the distance that we use times Fy to calculate the moment, okay? So Fy has a perpendicular distance from O, and that value is going to be used for computing the moment. The X component, Fx, passes through the origin and does not create blank, okay? So if we look here, if we take our Fx and we push it along its line of action, it's going to actually go through zero, the point 0. So if I put my finger on that origin and I push in that direction, it moves along the line. If I push in the direction of the Fy, notice the paper rotates. So remember what we said about moments? Moments is the tendency of a force to cause rotation. So there's a moment created here by the Fy, but there is not a moment created by the Fx. You see that? And if we even go a step further, knowing that when we calculate a moment, it has to have an offset perpendicular distance. We had a distance for that Fy component, which they're identifying as R. But for Fx, if we look through that, what would the offset distance from the origin be? 0, right? So 0 times whatever the magnitude of Fx is going to be 0. It's not going to cause a rotation. Okay, so that's another way to kind of know if there is a distance, it would be causing a rotation or a moment. But in the case of the X component, it's not going to cause a rotation. Okay, sorry. It's not going to cause a rotation. So on page 2, you've got perpendicular and rotation. Now, the theorem of moments is our next section in this chapter. Theorem of moments states that the moment of a force about a point is equal to the sum of the moments of the components of that force about the same point, okay? So we want to write the summation of the moments equation in variable form, okay? So to do that, it's going to be similar to what we did sum of the forces. So we're going to use that capital sigma, capital M, so sum of the moments, and then I'm just going to put this little cloud, all right? We need to identify the point that we're going to sum around. So in the diagrams that you create, you might have a letter A or a B or a C. So you would say the sum of the moments around, and you identify the point, okay? And then we would say equal to 0 or R or whatever it might be, okay? This would be equilibrium, but we might be equal to something. Now, because we are now looking at rotations, we are going to have a new convention. Up to this point, our convention has been the forces going to the right and up are positive, right? And this is how we write our convention. But now we're adding in moments, and moments have rotation, okay? So we have to identify a rotation to be positive, and that will be counterclockwise. Always. This is the convention that we're going to use in this class on every problem going forward, okay? We are not going to change the convention, all right? It just kind of keeps everything easy. That way I know that your positives are the same as mine and we're all consistent, okay? In actuality, you can change the convention. Let's say you have a bunch of forces going down, and rather than giving them all negatives, you're like, I'm just going to say positive is down. You can do that, but in statics, you're not going to, okay? Tyler, do you have a question?
I was just about to ask, is this common like workplace or?
Yes, this is the most common. And you're going to notice that in our textbook for McGraw-Hill, in this chapter, we're going to use the same convention throughout. Yeah. Yep. Okay. So let's look at our first example. This first example is a 4-1. It's on page 66 in our handout. So I'm going to turn the page here. Okay. And it starts down here and then it continues. And at the bottom here, it says, we want to find the moment of the 120-pound force at C, okay? So we've got a beam, if you would. And along the beam, we have point A on the left-hand side, 4 feet over point B. Then we have point C, and you'll notice that we have a 120-pound force directed up. And then we have point D. So it wants us to find the moment of that force at C about points A, B, C, and D. So we're going to sum, we're going to determine the moment at each one of those points, okay? So first thing we're going to do is we're always going to draw a free body diagram, and the free body diagram is going to come from this diagram right here. So down here, I'm going to just kind of peek ahead. I'm going to draw my diagram at the top of page 3 only because that way I don't have to keep turning the page. So I'm going to draw my diagram at the top here, and I'll have plenty of room to add my moments. My diagram, free body diagram and convention. So upper right-hand corner for this example, including the counterclockwise direction to be positive, okay? On the left-hand side, all the way over, when we draw a free body diagram, remember it's a simplified version of whatever we're looking at. So for this beam, there is thickness there, but we're just going to represent it as a single line, okay? And we're going to start with point A at the left. Then we're going to have point B here, point C, it's right about there, and then we'll point D here, okay? So I'm going to call this B, C, and D. You want to identify any distances. So I know that there's 4 feet in between A and B. There's 2 feet in between B and C. And then there is 2 feet between C and D. Okay. And then we're going to represent our force going straight up at 120 pounds. So this is going to be the diagram that we're going to use to sum or to determine our moment about each one of the points identified. So we're going to determine the moment about point A, B, C, and D. So the moment about point A, okay? So we're going to sum our moments about point A is equal to, okay? Now remember, a moment is force times distance. When you show a moment, when you show the product, you have to do this, okay? You're going to start with parentheses. You're going to put a little gap in front of it because we're going to give it a sign. But our parentheses, inside the parentheses is going to be force times distance. So our force is 120 pounds, right? 120. And you're going to put the units inside of the equation here. So units are going to be in all phases of the problem. And then it's going to be times the perpendicular distance. Now, for this problem, it's assumed that the 120 is 90 degrees to that beam, okay? So if we are summing our moments around A, that means that we are, if you would, putting our finger on A, and we are pulling in the direction of the force. If we get a rotation on our paper, that means we have an offset force causing a moment. And its perpendicular distance, if we see a 90-degree angle here, it's going to be 4 plus 2 to that force. You guys see that? So that's going to be 6 feet. Okay, I'm going to put the symbol inside here, and then usually at the end of my problem, I'll usually write out LB and then times feet. Okay. Now, remember, this also needs a direction according to my convention. So if I put my finger at A and I rotate in the direction, my paper goes counterclockwise. So that means that this is a positively directed moment. You have to give your moments a direction. Now, do not base the direction of the moment on the direction of the force. The force is going up. But remember, if we're summing forces, then we're looking at up, down, left, right. Okay? But when we're summing moments, we're looking at the direction that it creates based on that force about the point that we're on. So is this going clockwise or counterclockwise? This is going counterclockwise, right? So we're positive according to our convention. All right. So the sign out front here means counterclockwise. All right. Not a positive force. Right. Always put your parentheses around your moment. Force times distance. Okay. Now, since that's the only force causing rotation, there aren't any other forces, we would say then the sum of the moments about point A, we take 120 times 6, I think we get 720 pounds times feet, not pounds per feet. We didn't divide 120 by 6. We multiplied it. So the units have to multiply as well. Okay. So again, you could use the symbols if you wanted to, but I usually write it out. And then the box around your final answer. Now, because there's a positive out here, that's telling us the direction. So you don't have to put clockwise or counterclockwise out here. The positive relates us back to our convention. Does that make sense to everybody? Okay. All right, now let's sum our moments around point B. Sum moments around point B equal to. Now we're moving our finger to point B. And we're going to pull in the direction of the 120 pounds. Does it cause a rotation? Yeah, because there's an offset distance. So we are going to have a moment. It's going to be 120 pounds is the magnitude of the force. And then the distance is 2 feet. And the direction of rotation, the sign I'm going to put out front, what will that be? Positive or negative? Positive, yeah, because it's counterclockwise. So positive out front. Multiply that together. Our sum of our moments around point B is going to be 240 pound-feet. Pounds times feet. Force times distance. Sum our moments around C. Equals. I'm going to put my finger on C. And I'm going to pull in the direction of that force. Does it cause a rotation? No. And it's the only force on this. So that means that it's going to be, if you would, 120 times what? 0. So it's going to be 0. There's no rotation. When I put my finger at C, it's going to be a pull on that point or a push. So sum of the moments around C, 0. And then lastly at point D. We're going to sum our moments about point D equal to. Put our finger on D and we're going to rotate that force. Does it cause a rotation? Yeah, it does. So there is a moment. So I'm going to put my parentheses My force is 120 pounds. What's my perpendicular distance from D? 2 feet, right? So my distance is going to be times 2 feet. Now, this is where outside of our parentheses, okay? Make sure you have your force times distance inside. When I rotate this, this is going what? Clockwise this time. What is the sign I'm going to be putting in front of my 120 times 2? A negative, exactly, because it's rotating this time clockwise, okay? So our convention lets us know what's positive and what's negative, okay? So this means that our sum of our moments around D are going to be equal to a negative 240 pound-feet, okay? Now, you might say, well, torque, you say foot-pounds. But is moment a torque? Force times distance. It's going to be pound-feet. So get used to that. And that's how it's done. That's how it's done. Remember, it's not the same. So any questions on that one? Okay. Now, something I want to point out here is we see a positively directed force. That doesn't mean we're always going to have a positively directed moment. We saw it for A and B, but it went negative at D. And again, it's because of D went to the other side of that force, and then it caused a clockwise rotation. So don't assume because it's a positively directed force, it's going to cause a positively directed moment. Not going to always happen. I want to see, I'm not going to make you, but I encourage you to do the finger, on the point, rotate in the direction of the force to confirm that you, number one, have a rotation, but then it tells you which direction you're going in. So you put the appropriate positive or negative. Okay. All right. And there you have it. That's our first example. Good. The second example that we're going to do tonight is on page 67. This is going to be example 4.2. Okay. It says we want to determine the moment about point C, which is right over here. Okay. Due to force F. Okay. It's down here at the bottom at point A. It has a magnitude of 100 newtons and it has a angle of 60 degrees to the horizontal. All right. So we want to determine what is the moment that this creates, what is the magnitude of the moment, force times distance that creates about point C. Now we're actually going to solve this 2 ways, okay? We're going to first solve it by finding the perpendicular distance using right angle trig. And then the second way that we're going to solve it is going to be using components. Okay, you're going to notice that we're going to get the same answer in the end, but I want to show you both methods so that you can see how indeed, they're related and how to work those. So the first way we're going to do it is going to be how we see it here. And we're actually going to find the perpendicular distance from C to the force. So first of all, I'm going to draw my diagram on my paper here. Now I have quite a bit of room here. So what I think I'm going to do is I'm going to, again, start on the second page here, just so that I'm not like always flipping back and forth. And I'm going to draw my free body diagram. And this is example 4.2. Now on the previous page, you're going to notice that it kind of gives us a little procedure. We're going to first draw our free body diagram. We're going to include our new convention. We're going to find the moment about C due to the force at the magnitude of 100 newtons applied at point A on the bracket. And like it says here, you're going to solve it in 2 ways. So we're going to do the first way as we see it. So I'm going to put my convention in my upper right-hand corner so I know exactly what's positive. So don't forget to add the rotation because we're going to see moments here. And then I am going to draw my bracket. Okay. So free body diagram of the bracket. Going like this. This is going to be my point C. This is 0.8 meters. This is a little shorter, 0.6 meters. And then down here is point A. We kind of extend this. Don't have to draw this to scale, but I've got a protractor. So I've got 90, 30 degrees, So it's going to be coming off at a 60-degree angle from vertical. Okay. So I know this is my force F, and F is equal to 100 newtons. And I know that this is 60 degrees. Okay. Now, using the information we have here, the way they want us to solve this is they want us to go from point C, and they want us to find this perpendicular distance D, okay, to that. So we're going to be taking 100 times that distance. So to get the moment, we got to find the distance D from C to the perpendicular to force F, okay? And again, it has to be perpendicular, okay? So to get this, what we're going to do is we're going to kind of extend this triangle. We're going to kind of go up like this. I'm going to kind of use a dashed line so you can see that this is really along the line of action, okay? Just taking that and going backwards. And the same thing up here along that horizontal. Okay. And what we end up creating here then is, I have a highlighter in here, I do. I end up creating a large right triangle. Do you see that? Okay. Now, if we look at our bracket, they identify this as point B. And then if you look at part B figure, they call this point, this intersection point out here, point E. Okay. Now, why do we want to do this? Well, we want to find this perpendicular distance here. So we've got to use what we have. Now, what we do have, you're going to notice that there's another right triangle here. Do you see this right here? Right? And if we know that this is 60 degrees, okay, using your geometry skills, do we know what this is? So it'd be 30 degrees. Yeah, be careful, right? So we know that this is 60. This corner would be 60, right? So this one is going to be 30 degrees. Yeah. Okay. Now, if we know that this leg right here is 0.6 and the side opposite I'm sorry, the angle opposite is 30 degrees, and I want to find BE. What trig function would I use? This is a leg, and I've got an angle. Sine, cosine, or tangent? What are we thinking? It would be tangent, right? Sine and cosine need a hypotenuse, right? The hypotenuse is here. We want to find BE, and we know the side opposite. So we can say that tangent of 30 degrees is going to be equal to side opposite 0.6 meters divided by BE. Okay. So solving for BE then, that means I'm going to multiply it up here, and then the tangent 30 is going to come underneath. So rearranging, BE is going to be 0.6 meters divided by tan of 30 degrees. So BE, what do you get?
1.039.
That's what I got. Yeah. 1.039. And what are my units here? It would be meters. Meters did not cancel out. Remember, you're putting your units in all phases of the problem. So this is going to be 1.039 meters. So that means the distance from here to here is 1.039 meters. Now, do you see how that is the hypotenuse of the really big triangle? You see that? So this is a 90-degree angle right here. This is 30. I have my hypotenuse, and I want to find D. What function am I going to use here? 30 degrees, D, hypotenuse. Side opposite, hypotenuse. Sine, cosine, or tangent, people. Virtuals. We're going to ask the virtuals. We're going to put them to work. Virtuals, am I going to use sine, cosine, or tangent to find D if I know 30 and the hypotenuse? Which one? In the room, sine.
Sine.
Yep, that sounds good. Thank you, Josh. Okay, so we're going to use sine of 30 degrees. Sine of 30 degrees is going to be equal to side opposite, which is D, divided by the hypotenuse, which is 0.8 meters plus 1.039 meters, all underneath there. Okay, so this is the full hypotenuse down there. So if I multiply that up, multiply that times the sine of 30, D is going to be equal to sine of 30 degrees times, I'm just going to add those two together, 0.8, 1.039 plus 1.839 meters. What do we get for distance D? 0.919. It's good to me. Meters. Now, that's not our final answer, is it? Because what are we trying to find in this problem? We're trying to find the moment about point C, right? So if C is up here, our force is here, we just solved for the distance, okay? So now we're going to use that distance. We're going to sum our moment around point C equal to, and we're going to take the 100 newtons, that's the magnitude of our force, times the perpendicular distance, 0.919 meters. Notice I have the units in back of each one of those quantities. Make sure you put it in there. I don't want to see 100 times 0.919. Points off, okay? Units in all phases of the problem. Because you want to see how these combine and or cancel sometimes, okay? And if you end up with the correct units for something that you're trying to solve for, so we know that moments are going to be force times distance. Now, when you get the correct units, you know you set up the problem correctly, which is everything. It's everything, right? If you don't set up things properly, you don't have a chance. Units help you to confirm and have confidence in how you did your setup. Okay, now out front, we don't have our moment fully defined. We know the force times the distance, but if I put my finger on C here and I rotate in the direction of that force, what is the sign that I'm going to put out front? Positive or negative? Negative, because it's going clockwise, right? So you have to put the negative based on the direction of rotation. Because this right here, down and to the left, what would be the sign of that force? Doesn't go along with our X or Y, right? We really don't know. So we've got to put our finger on C, we've got to rotate it and then compare it to our convention. And in this case, that's clockwise, so it's negative. So it looks like our moment around C is going to be, move that, what, 2 places to the right? 91.9 Newton per meter. Yeah? Yeah? Really? Jesse? It's just newtons times meter because I multiplied. I didn't divide. Sounds like it would be right, but it's wrong. Don't do it. Resist the urge. There you go. Oh, put a negative out front of there too, because the negative tells us its direction. So don't forget, negative 91.9. Okay. Any questions on this? Okay. This is the first way that we solved it. Now we're going to solve it the second way. The second way is we're going to draw that same bracket, okay? But we're going to break that force into X and Y components. And we're going to see how that works. So I'm going to turn the page, okay? So we're going to do this a second time. So this is still example 4.2. I'm going to put my convention again. This is a new problem technically, okay? Up in the upper right-hand corner. And I'm going to draw now my bracket C to B to A. So this is C. This is going to be A. And this is going to be B. We know C to B is 0.8 meters. We know B to A is 0.6 meters. We know that coming from horizontal, we got 60 degrees. I'm sorry, coming from vertical is 60 degrees. And I know that F is equal to 100 newtons, and that this is 60 degrees, right? So now what we're going to do, and I'm just going to kind of draw the X and Y axis through point A. We're going to break F into X and Y components, okay? And we're going to put them at point A here. So let's draw them first. Okay. And then draw this going up. And we're going to put each one of those components along the x-axis, along the y-axis. Okay. And we're going to call this fx and fy. Now, we need to calculate the magnitudes of the X and Y components, and we'll be able to do it. We're given the hypotenuse of 100 newtons. We know that this angle is 60. Be careful. This is not the standard placement if you want to do cosines with the X's and sines with the Y's. If you want to do that, you need to use 30. If you use the 60, the sine is going to be with the X and the cosine is going to be with the Y. So I'll let you decide how you want to do that. So our first step here is going to be components. So my f of x is going to be equal to sine of 60 times 100 newtons. Make sure you put your units in here. Fx is equal to Notice I didn't put the negatives in front of either one of these. Yes, they're pointing to the negative direction, but we see it the way that we have our arrowhead. So you don't have to put the positive or the negative in front of either one of these, and I actually discourage you to do that. Let the arrowhead give you your direction. So did everybody get Fx is 86.6 and Fy is 50 newtons? Make sure you have your units in your equation as well as your final units here, okay? If I see just 86.6 and 50, points off, okay? Units in all phases of the problem for every one of your answers, even if it's not a final answer. We don't want them to magically appear. They're not lucky charms, okay? Units are not lucky charms. They might be magically delicious. You guys know what Lucky Charms are? Do they still have them?
Yeah.
Okay, I don't buy them.
I had some.
I remember them being magically delicious. You had some last week? Oh, good. When I've said this for many years, I talk about radians that way. And one time I had one of my students bring me in just the bag of the Lucky Charms, the little marshmallows and he's like, I was somewhere and they were selling just the Lucky Charms. Did you ever see that? It's amazing. I'm like, cute. So anyway. It's kind of fun. All right. So we've got our units on here. So now what we're going to do is we are going to sum our moments, but we're going to use the components now. And the reason we're going to use the components, it kind of got convenient because notice we have horizontal and vertical distances that we can't use with the 100 newtons, but now we can with our horizontal and vertical components. Okay. So let's see how we do that. So we are going to go down here and we are going to sum our moments around point C, okay? Sum our moment around point C. We're going to go up here. We're going to put our finger on C. We are not going to use the 100 newtons, but we are going to use the Fx, okay? Fx. Does Fx cause a rotation? Yes, it does. So we are going to start here. We're going to start with a parentheses. I'm going to leave a little space because we'll add our sign in just a minute. The magnitude of Fx, which is the force, is 86.6 newtons times Let's figure out our perpendicular distance. From C, if we go straight down and we make a line perpendicular to the line of action of our FX, what is this distance right here? 0.6. Do you see that? 0.6. So that's going to be 0.6 meters. Put the units in there. And then let's go back up. We have to put a sign in front of our moment. FX is rotating in a clockwise direction. So we're going to put a negative out front. Okay. Remember, this is clockwise direction. Yes, FX is going in a negative direction for the force, but we're not summing forces. We're summing moments. I can't emphasize that enough. You almost have to think, am I in moment mode or am I in force mode? If I'm in moment mode, it's the direction of the rotation, not the direction of the force. Okay. Put my finger back on C, and now I'm going to pull in the direction of Fy. Does Fy cause a rotation? Yes, it does. So that means it's going to be Fy's magnitude, which is 50 newtons this time, times Fy's perpendicular distance to C. We're going to back this force up along its line of action. And do you see how 0.8 is the perpendicular distance to Fy? See that? Remember, we can move that force anywhere along its line of action. Principle of transmissibility, and not change the net effect on the body. Okay. So we're just going to back this up until we can get a perpendicular distance, and our perpendicular distance is going to be 0.8 meters with the 50. And then again, the direction out front is going to be positive or negative? Negative, because it's counterclockwise again. I'm sorry, clockwise. It's clockwise. Right. So now we just multiply, add, subtract, right? Or subtract these two. And what do we get for the total moment about C? We should get something close to what we had earlier.
Negative 91.96
And
Newton meters.
we had negative 91.9, right? Yeah, before. And that might have, if we would have held it maybe one more decimal place. Now, so I'm done, right? Is that good? I have my negative in front. I have my 91.96. Anything
meters.
else? Well, what do I need? I heard
Newton
it.
meters.
Newton meters, my units. Don't forget to add your units. Okay. So good. Okay, now this is everybody's favorite class, right? I'm going to get you by the end. It will be, I promise. I might have to start bringing food. All right. All right. Any questions on example 4.2? Again, we did this two ways. The first way we looked at this, we found the perpendicular distance from the original force. Okay, the force was at that 60-degree angle. We had to do some trig, not hard trig, but we had to find that perpendicular distance, and we found the moment based on force times perpendicular distance. Then we did it a second way, where we broke the force into its components, and really using information that we were given on the distances, we then had to do an extra moment, if you would. It wasn't just one moment. We had two here because we had to use both the X and the Y components, but then we used the perpendicular distances that were given on the bracket, and we ended up with the very same answer. So when you approach these problems, the point of this is sometimes you might find, yeah, I'm going to use components. I think that looks good. Or you might be like, I'm going to use the perpendicular distance because, you know, that seems to make sense for this problem. Both will render you the very same answer. Okay. We tend to, and I tend to, and either book here tends to use components going forward. So you can kind of see it works out either way. All right. Let me look at the next problem and see what that looks like. Let's do one more example problem tonight, okay? And then we will, I think, be in a good place. So the next problem we're going to look at is on page 6, example 4.3, which is on page 69 in our handout. This is going to be the problem that we're going to look at. So it says, determine the moment of the three forces that act on the truss below. And we want to find the moments about point A and point D. So we're gonna do two moment equations. And here is what we're looking at in terms of the actual problem itself. Okay. So what we're going to do is we're going to draw this truss. Okay. And the 2 points that we're going to sum around are points A and point D. And the three forces that we see here are F1, F2, and F3. So what I'm going to do is I'm going to draw our free body diagram, and it's going to end up looking just like this. So if you go over to part C here and you want to kind of look there, that's what we're going to be using, and then identifying, summing our moments around these 2 points. Notice that we're going to break that F1, which is at an angle, into its X and Y components. Okay, so I'm going to start by drawing the diagram and adding my convention. Okay. So you can follow along here. Now, you don't have to use straight edges. I end up using them just because, but if you're ever like, you feel like it helps. I will say that. Sometimes trying to freehand some of these is a little crazy. So here's point D. Here's point A. So again, kind of simplifying the views here, but we want to identify any points, dimensions, and forces that were given. So this up here is point B. Okay. This down here is C. This is E. And this is point F. Okay. As far as distances, we know that this is 4 feet, 4 feet, and then any of these heights are 5 feet and 5 feet. We have a force going straight down at F, and that is 8 kips. What's a kip again? Do you guys remember? 1,000 pounds. So it's technically 8,000 pounds, but we can make it shortened version by calling it a kip. This is going to be theta, and this is 10 kips. And then we have another force going to the right, and this is going to be 5 kips. I'll let you guys get the diagram going. Don't forget your convention. Four feet, and this is 4 feet. So all the horizontal members in the triangles are 4 feet, all the verticals are 5. Now, we can see that we're going to have to break that force up at point B into X and Y components, but we need to know what the angle is. We can see that the line of action of that force is along, the member here in our truss. So when we look here, we've got a bunch of right triangles, and this angle right here, okay, this one right here, would be the very same angle of theta, okay? So if we look at our triangle here, to find theta, we know the side opposite and the side adjacent. So we can use the tangent function, right, to calculate theta. So we're going to say tan of theta is going to be equal to, and we're going to use the sides of the triangles down in the truss, 5 feet, side opposite, over 4 feet. Feet cancel out, which makes sense. And when we use the inverse tangent, what do you guys get for an angle?
51.3 degrees.
Yep, 51.3 degrees. And that's, if you look at our example problem, that's exactly what they get. Okay. So that means this is going to be the angle then that we use for our components. Now let's draw our components. Okay. So go ahead and put your X and Y components in place here up on the top. Okay. And put your arrowheads the way that you think they should go. Sometimes these might be a little like, if you're unsure of whether you should put the X and Y up, down, or left or right, just repeat to yourself what the direction of the 10 kips is. The 10 kips is going down and to the right. So that means that your Y should go down and your X should go to the right. Does that make sense? That's how I kind of put it together. So my Y component, and we'll call this, I think they called that one F1Y. I'm going to call this F1Y because this was called F1. Okay, they called the 10 kips F1 on the diagram. And then our F1X is going to be going to the right. Okay, and we'll use that for calling out the components then. The other two forces are already vertical and horizontal, so we don't need to do components there. So let's find F1X and F1Y. So go ahead and solve for those components. And then 252 and 4. So again, notice that I'm not putting a negative Fy. I have it identified with the direction up here, even though it's going down. I just have the absolute value, if you would, for the magnitude of the F1Y. So 7.8, I got 7.804 and 6.252. I added the extra decimal place. So those are the magnitudes of those two forces. Now that we have those forces broken into their X and Y components, we now can sum our moments around points A first, and then we're going to sum around D. Okay, I'll give everybody a chance to catch up. Okay. So our next step here is to sum. I'm trying to remember on the next one. Oh, I'm gonna have to get them both in here. So I don't have a ton of room. So sum the moments around point A equal to. Okay. So that means I'm going to put my finger on A. All right. And I'm going to start with my 8 kips. Okay. My 8 kips is offset. It's going to cause a rotation. So when I look here, this is going to be 8 kips times 4 feet. Do you see that? Here's the perpendicular distance to the 8 kips. Okay. Now, when I rotate this, this goes in a clockwise direction. So I put a negative out front. So remember, your moment has to be inside of the parentheses, force times distance. Outside the parentheses is the sign, and that's the sign for the direction that it's rotating. So negative out front. Put my finger back on A, and I'm going to pull in the direction of the 5 kips. Does it cause a rotation? No, it's not going to be included. So don't even put 5 times 0. Just leave it off, okay? It's not causing a rotation. We're not going to worry about it. So it's not included. I'm going to go back up to F1. And we're going to pull in the direction of the Fx component, that F1x component. Yes, it causes rotation. So the magnitude of F1x is 6.252 kips. Times perpendicular distance. So from A, now this one, if I move this back along its line of action and I draw a line straight up, you see how straight up would be my perpendicular distance to my X component? Okay. What's the distance going straight up? 5 feet is the perpendicular distance. So 5 feet. Now, when I put my finger and I rotate in the direction of F1x, it goes clockwise. So negative out front. Everybody see that? And I've got one more force to consider. I'm going to go back up here, put my finger on A, and I'm going to pull in the direction of F1y, causes rotation. Now, if I push along F1y, what's my perpendicular distance? 4 feet. Do you see that? Remember, I can push 4 along anywhere, or I'm sorry, I can push F1y anywhere along its line of action. And then when it meets with A, it's kind of like its radius or its distance. So magnitude of F1y, 7.804 kips times perpendicular distance of 4 feet. And then again, it's going to go in a clockwise direction. So negative out front. So a couple things when you write this out. The summation symbol in front of the capital M, that's sum of the moments. Sub A tells me the point I'm summing around. Equal to each one of your moments. There's 3 moments here. You're going to see 3 parentheses that inside the parentheses, it's going to be force times distance. And you have your units in each one of those parentheses. Additionally, you have a sign out front that signifies the direction of the rotation about that point, and it's positive or negative according to your convention. Okay? So make sure you have all of those elements in this line. If you don't have units, points off. If you don't have the positives and the negatives, points off. If you don't have sum of the moments around A, points off. Okay? All of those elements are really important. All right, what do we get for our value of the total moment about point A? It's going to be negative something. You get 94.5. That's what the book has, 94.5. And then what are our units? Kips, feet. Kips times feet, not kips per foot. And with the negative, that lets us know that if we go back up to our convention, oh, that means that around A, if I would hold it there, the tendency is going to be in a clockwise direction based on those forces. So good. I'm excited for you guys. You get to do the homework for this. Aren't you? Aren't you looking forward to it? Like, thank you. Ready for some of the moments around D? Do you want to try it by yourself? Go ahead. Try to do some of the moments around D, and then we'll compare. I'm going to give you 1 minute to sum your moments around D. And if you don't want to, and you want to wait for me, then just wait for a minute. Check them out. Remember, you're going to put your finger on D. Now you're going to rotate in the different directions and see what happens. All right, let's start looking at it. There was no hurry. If you didn't get completely through it, that's okay, or keep working on it, but I'll get started here. So D, I'm going to put my finger on D, and I'm going to start with my 5 kip force. It is going to cause rotation. So the magnitude of the force is 5 kips. The perpendicular distance, if I come down to D here, straight down, that perpendicular distance is going to be 5 feet. And when I rotate, it's going to go counterclockwise. So sum my moments around D. In parentheses, it's going to be 5 kips times the perpendicular distance of 5 feet. And because it's going counterclockwise, tells me that it's positive out front. So make sure you put your sign. You can do an assumed positive as your first value, but I don't know. I think it's nice to intentionally. I won't never take off points for that, but make sure that you check to be sure that it is indeed positive. All right, the next one. Put my finger on D. I'm going to pull in the direction of the 8 kips. This also is causing a rotation. All right. So if I back this up all the way, so D is here. If I go this way and I back this up, what's my perpendicular distance from D to where the 8 kips would be? Or if you come straight down here, this is my perpendicular distance. What's that distance? 8 feet. Yep. So my moment is going to be 8 kips times 8 feet. Okay. In parentheses, force times distance. And then as we look up here, if I rotate in the direction of that 8 kips, that's going to go counterclockwise. So positive out front. There we go. Going back up. D, I'm going to do my F1X. If I push on F1X, is it causing a rotation? No. And indeed, it's going to go right through the point. So there is no moment. There is no offset distance. So we're not even going to include it. Don't even worry about it. Okay. Put my finger back on D. The Fy, though, does cause a rotation, right? So the Fy is going to be a counterclockwise rotation. So it will be positive. Its magnitude, 7.804. And its perpendicular distance, 8 feet. Okay. So positive 7.804 kips times 8 feet. Okay. Now, as we look, I think that exhausted all of our forces. So we're ready to sum our moments around point D. I'm hoping you got a positive 151.5 or very close to that kip feet. And we're going to put a box around it. Remember, the positive out front corresponds to the direction of rotation. Okay, so it's telling us that it's going counterclockwise. Right. So any questions on this example? So it wanted us to sum the moments around each one of those. We drew our free body diagram, put our components up there, and then found the perpendicular distances and applied the convention. Okay, so that's where we're going to stop today for our practice problems. All right. And indeed, if you're in the room here and you're filling this out along with me, this is what you're going to be having even for the practice problems. For those who are virtual, you just have to make sure that you write this stuff out if you didn't get a chance to do the printout. All right. So I'm going to stop the recording here. Don't go anywhere.